In this video, we're going to talk about graphing logarithmic functions. Our learning targets for this video, we're going to find intercepts and asymptotes of logarithmic functions, which we already did a little bit. We're going to determine the range and domain of logarithmic functions, and we're going to write and graph transformations of logarithmic functions. For the first part, we're given y is equal to 10 to the x power. That's an exponential function. This is an exponential function here. We're going to graph this thing, this exponential function. We've done this a million times, graphing exponential functions. We're going to set up a table to start. So we're going to set up a table. So I'm going to do for y is equal to 10 to the x power. I have a table. I'm going to pick x values to plug in and see what I get for y. I'm going to plug in -1 for x, and if I plug in -1, I'm going to have 1 over 10 for y. If I plug in 0 for x, I'm going to get 1. 10 to the 0th power is 1. Anything to the 0th power is 1. If I plug in 1 for x, I'm going to get out that I'll have 10 to the first power, which is just 10. Okay, from there, I'm going to determine what's my horizontal asymptote, because I know that's something I'm not going to touch, so I'm not going to touch the horizontal asymptote, and in this case, the horizontal asymptote is y is equal to 0. I have no vertical shift for y is equal to 10 to the x power. There's nothing being added or subtracted at the end, so I know that I'm automatically going to start at the x-axis for the asymptote, and that is y is equal to 0. Horizontal asymptote. From there, I want to plot my points. So I have -1 and 1/10, and I have 0 and 1, and I have 1 and 10. 1, 2, 3. It's like up here. I'm going to connect these, making sure that I don't touch that horizontal asymptote. And this is my graph. The domain of this graph is all the included x values. Since I see arrows going in both directions, on the left and the right, I know that I'm going from -infinity to +infinity for all my included x values. For the range, all my included y values, I know that the lowest y value included is something just a little bit greater than 0. 0 is not included, but just a little bit greater than 0 is. So I'm starting at 0, putting a parentheses on it to indicate that everything just a little bit greater is included, and I'm going to end my interval with +infinity because that graph extends and keeps going up and up and up. For the next part, B, I want to find the inverse. I want to find the inverse of that exponential function, y is equal to 10 to the x power. All I'm going to do is switch the x and the y. So instead of y is equal to 10 to the x power, I'm going to have x is equal to 10 to the y power. And I want to get that, after I switch the x and y to find the inverse of equation, I need to get the y by itself, because y is always my output for a function. There's no other way to do this than to convert this exponential form that I see here into logarithm form. So that's what I'm going to do. I know that this is my base, this is my exponent, and this is my answer. So when I write in log form, I'm going to write log base. The subscript is going to be the base, which is 10. What goes inside of the logarithm is the answer, which is x, and that's going to be equal to the exponent, which is y. I know that log base 10 of x is it's the common logarithm. So if I see log base 10 of x, I know that's actually equal to just log of x. The log of x that I see in my calculator, that's to base 10. So if I see log base 10 of x, I don't need to write the 10. I can just write log of x. I'll just put log of x is the common log. It's the common logarithm, and the common log is to base 10. And if I do that, what I'll actually write instead is log, I'll write log, I won't write the base, I'm just going to write x, log of x is equal to y. Or I'm going to switch this up to look like this. Y is equal to log of x. So I just flipped my sides and got rid of the subscript. So this is my inverse of y is equal to 10 to the x power. For D, I want to make a table and graph that the inverse function I just came up with from part C, and I want to do it on the same grid that I did for the exponential function y is equal to 10 to the x power. So I'm going to pick values for x to plug in and see what I get for y. And I'm going to use this equation here. So I'm going to do, log base 10 of x is equal to y. What I want to do is I want to pick values for x to plug in that are powers of 10. That way it's going to spit out whole numbers for me for y, for the exponents. So if I plug in, let's say 10 to the negative first power, if I plug that in, I'm going to have log base 10 of 10 to the negative first power is equal to what? And what this is really asking me is, what do I have to raise 10 to get 10 to the negative first power? And that is negative 1. So I'm going to put negative 1 for y. That's my y value. That's my exponent. Another thing I could pick is 1. If I plug in 1 for x, I'm asking myself, what do I have to raise 10 to get 1? And it doesn't matter what the base is, to get 1 from any base, I would have to raise it to the 0th power. So if I plugged in 1 for x, I would get 0 for y. Another one I could do is log base 10 of 10. I'm asking myself, what do I have to raise 10 to get 10? And that is the first power, so it spits out 1. If I plug in 10 and 1 I have. I'm going to put this graph on I'm going to plot these points onto this graph. So I'm just going to rewrite 10 to the negative first power in terms of, I'm going to make it a fraction. So I'm going to make another table here. Just another table. I'll line it up with the other one. And this is going to be for y is equal to log base 10 of x, or you could also write y is log of x. 10 to the negative first power is 1 over 10. So I have 1 over 10 and negative 1. I have 1 and 0, and I have 10 and 1. Before I plot these points, I want to talk about what's my asymptote going to be. Because I know this is the inverse of the original function, I know I'm going to have a vertical asymptote instead, since everything about my x's and y's flips. Instead of a horizontal asymptote, I'm going to have a vertical asymptote. Instead of it being at y is equal to 0, it's going to be at x is equal to 0. And I'm going to draw that dashed asymptote and label it my vertical asymptote. And then I'm going to plot these points. So I have 1 over 10 and negative 1. I have 1 and 0. And I have 10 and 1, which is like here somewhere. And then I'm going to connect these and make sure that I don't touch the vertical asymptote. As you can see, these two graphs look like a reflection over the line y is equal to x. So I've graphed them correctly, because that's what inverses are supposed to look like, a reflection over that line. Another thing that I have that I want to do is find the domain and find the range. So the domain of this blue function, I'm seeing that my x values, all that are included, are from 0 to infinity. And for the range, I know I'm including everything from negative infinity to positive infinity. I want to write down a few things that I noticed between these two graphs and their tables and all the information that goes along with them. And one thing I noticed is x and y are flipped. X and y are flipped. That's true about all the points that I look at that are graphed, all the points in my table. Everything about x and y is flipped. I also notice it's a reflection. The original and the inverse are a reflection about the line y is equal to x, as inverses always are. The domain and range, I also notice, are flipped. So the domain and range are flipped. And that makes sense because everything about the x's and y's are flipped. And because of all of this, I know that, and I'm going to write it up here, y is equal to 10 to the x power, and y is equal to log of x, or log base 10 of x. Base 10 of x are inverses. because all of those things are true. Even though I did like go through the steps of, and I know it's my inverse, I can see this also from the graph that I have here in the tables. Here I have the definition of a logarithmic function with base a, and there's just some important facts that you need to know about logarithms. If this is the general form that I have for a logarithm, y is equal to log base a of x, where a is some number base. X, the thing inside of the logarithm, no matter what your base is, the thing inside the logarithm has to be a positive number, so x has to be greater than 0. Another thing that needs to be true is the base has to be greater than 0 for logarithms. The base has to be greater than 0. It can't be a negative number. And the last thing that needs to be true is a cannot be equal to 1. If you have the general form y is equal to log base a of x, you can convert that to exponential form. X is equal, with all of those things true, you can convert to exponential form. X is equal to a to the y power, and we've talked about this already. The way that you pronounce this, function, f of x is equal to, what did you see on the right-hand side? You read the right-hand side as log base a of x. You say of because this x is inside of the logarithm. The next thing we're going to do is talk about transformation rules. These are the same as every other function we've looked at thus far, most similarly to exponential functions, because you do need to keep in mind what your base is before you can use transformation rules. For the purposes of explaining the transformation rules and just going over them, I'm going to let the parent function be to base 10. So I'm going to do for base 10. And the parent function would be y is equal to log of x, or y is equal to log base 10 of x. To that function, so if I see extra stuff to that function, and that extra stuff is on the outside of the logarithm, I'm adding or subtracting something. Let's start with adding. If I'm adding a number outside of the inside of the logarithm, I'm going to use the transformation that every one of my points is moving up that number of spaces. If I see y is equal to log of x, and then the extra stuff is that I'm subtracting a number on the outside, I know that that means that I'm moving down that number of spaces. Say moving down that number of spaces. If I see y is equal to log of x, but inside of the logarithm I'm adding a number, then, so in parentheses I see x plus a number, that means I'm going to be moving all my points to the left that number of spaces. And if I see y is equal to log of x minus a number, I know that that means I'm going to be moving to the right that number of spaces. Remember, if you see inside with your input that you're adding something, it actually means you're moving to the left. If you're subtracting something inside, it means you're moving to the right. Another thing I might see is if I have y is equal to negative log of x, I know that that means that I have a reflection over the x-axis, and I know if I see y is equal to some number in front, log of x, and maybe I should use a different, instead of a, I'm going to use something I haven't used before, so c. If I see a coefficient in front of the logarithm, I know that there's a vertical stretch or shrink. So a vertical shrink or a vertical stretch. Tips for graphing logarithmic functions. We're actually going to use exponential functions to graph logarithmic functions. We're going to start with what we're going to call our parent inverse exponential function. Of the logarithm that we want, and then we're going to go to just the parent logarithmic function, so the parent log function, and after we do that, we're going to apply transformations. We're going to apply the transformations to get us our final log. Another thing to keep in mind when we're graphing logarithmic functions is to use horizontal shift, not the vertical shift this time, but the horizontal shift to get the vertical asymptote, since we're going to have vertical asymptotes for logarithm functions. To find the vertical asymptote, we're going to use the horizontal shift. what's happening to the x. For these functions, I'm only going to do a couple of them, and then I want you to do the other ones on your own. I have y is equal to log base 2 of x to start. That is the parent function for base 2 for logarithms. To find the table for that, we're not going to pick values for x to plug in and see what we get for y. We're going to start with our parent exponential function. We're going to start with the parent exponential inverse function. And that is going to be base 2 for an exponential function. So y is equal to 2 to the x power will be our parent exponential. And we'll pick values -1, 0, and 1 for x to plug in, and that will give us 0.5, 1, and 2 for our y values. From there, that's our parent exponential. Then we're going to go to our parent logarithm. So our parent log in this case would be the inverse of y is equal to 2 to the x power, which is y is equal to log base 2 of x. And what we're going to do to find that table is just flip all the values that we have here for our x and y. So instead of -1.5, we're going to have 0.5, -1. Instead of 0, 1, we're going to have 1, 0. Instead of 1, 2, we'll have 2, 1. And I don't have any other transformations happening here, so I don't have to apply transformations. This is my parent log for base 2. I'm going to first decide where my vertical asymptote is, and since there's no horizontal shift, there's nothing happening to that x inside of the logarithm, I know it's going to be at x is equal to 0. I know I have vertical asymptotes for logarithm functions instead of horizontal. So I'm looking at the horizontal shift for them. I'm going to do 0.5 and -1. I have 1 and 0 and 2 and 1. And I'm going to connect these, making sure I don't touch that vertical asymptote. The domain is everything from 0 to infinity, and the range is always for logarithm functions, -infinity to +infinity. For the second example, I have y is equal to log base 2 of x minus 2. I'm going to start with my parent exponential function. I'm going to start with the parent exponential, which is the inverse of whatever my parent log is. And it's going to be, for this example, also base 2. So it will also be y is equal to 2 to the x power. You should do this for everyone, even though you're probably going to see base 2 a lot. I would always start with your parent exponential function, which is -1, 0.5, 0, 1, 1, 2. Actually write it out so you don't get confused, because sometimes, or what I see a lot of the time, is that if kids start with this, if they start with the parent log, they actually write this table instead of what they're supposed to write, which is the inverse. So it helps to write every single step of this to do it correctly. The next thing I'll have is the parent log, which in this case will be, instead of y is equal to 2 to the x power, the inverse of that, which is y is equal to log base 2 of x. I know I'm flipping all these x's and y's. I've already done this. So I'm going to have 0.5, -1, 1 and 0, and 2 and 1, and I'm going to leave enough space because I see there's a horizontal shift here that's going to affect my x values. I see this -2 inside. Now I'm going to apply my transformations. So I have that -2 inside, which means I'm moving everything to the right 2. That's going to affect my x values, which tells me that I'm going to add 2 to all x's. If I'm moving to the right 2, all my x's get added 2 to them. And then my final log, so the log I wanted to end up with the transformation is y is equal to log base 2 of x minus 2. It includes the transformation of moving everything to the right 2. And I'm just going to apply what I just did, the transformation. So I'm going to have 2.5 and -1. I'll have 3 and 0, and I'll have 4 and 1. Before I plot these points, I'm going to determine where my vertical asymptote is based on the horizontal shift of moving everything right 2. Instead of it being at x is equal to 0, my vertical asymptote is going to be at x is equal to 2. That's my vertical asymptote. So x is equal to 2 is my equation for the asymptote. I'm going to plot these points. So I have 2.5 and -1. I have 3 and 0. I have 4 and 1. I'm going to connect these, making sure I don't touch that vertical asymptote. For my domain, I'm starting with my asymptote of 2, going to infinity, and for range, always negative infinity to positive infinity for logarithm functions. The next one I'm going to do is I'm going to go down here, and I'm going to do this one. Whoops. I'm going to do this one here. I see 2 transformations here. So I have to be doing 2 transformations to my apparent logarithm. I'm going to start with my apparent exponential. Whoops. I'm going to start with my apparent exponential. My apparent exponential again is base 2, so y is equal to 2 to the x power. Same thing as I had before, -1, 0, and 1. I have 0.5, 1, and 2. If I find my apparent log from that, I'm going to have y is equal to log base 2 of x. That is going to be 0.5 and -1, 1 and 0, and 2 and 1. And I know the 2 things I'm applying is I have this +2 inside means I'm moving everything to the left 2. So I'm subtracting from my x's by 2. And then I have this -3 on the outside, which means I'm moving down 3. All my points are moving down 3, which means I subtract from my y's as well. Subtract y's by 3. So for my final log, is going to be for the equation is going to be y is equal to log base 2 of x plus 2 minus 3. That includes my 2 transformations and is the equation I want. I'm going to be subtracting 2 from all of my x's and subtracting 3 from all of my y's. And my new points are going to be, when I do that, I'm going to get -1.5 and -4 for my first point, -1, -3 for my second point, and 0 and -2 for my third point. I'm keeping in mind what's happening horizontally for where my vertical asymptote is going to be. Everything is moving left 2, so from x is equal to 0, I'm going to have x is equal to -2. That's my vertical asymptote. I'm going to plot these points, so I have -1.5 and -4. I have -1 and -3, and I have 0 and -2. I'm going to connect these, making sure I don't touch that vertical asymptote. The domain is the asymptote, so -2 to positive infinity, and the range is always -infinity to positive infinity for these graphs. The last one I'm going to do is this one here. I have y is equal to log base 2 of x plus 1. I'm starting with my parent exponential, which again is the same. I have y is equal to 2 to the x power. This is, I'm using -1, 0, 1. I'm going to have 0.5, 1, and 2. My parent log is the same as well. Parent log is y is equal to log base 2 of x. I have, that's 0.5, -1. I have 1 and 0, and I have 2 and 1. And I know the 2 transformations I see are this +1 tells me I'm moving to the left 1, which affects my x's. I'm subtracting from all my x's, subtract 1 from all x's. And I also have this negative in front, and that negative in front tells me, and I didn't have this, the negative in front tells me I'm multiplying all y values by -1. And I apply these, I'm going to have my final log. My final log is going to be for this equation here. And I'm going to do -1 to all my x's, multiply all of my y values by -1. And I'm going to end up with, my table will be, I have -0.5 and 1. I have 0 and 0, and I have 1 and -1. And I know my vertical asymptote is going to be at -1, since everything's moving to the left 1. And I'm going to plot these points, -0.5 and 1. I have 0 and 0, and I have 1, -1. I'm going to connect these, making sure I don't touch that vertical asymptote. And so my equation for my asymptote is going to be -1. The domain is -1 to positive infinity, and the range is -infinity to positive infinity. If I'm given y is equal to e to the x power, and I want to graph that thing, I'm going to make a table, and I'm going to pick values for x to plug in and see what I get for y. I'm going to pick -1, 0, and 1. If I plug in -1, I'm going to get about 0.4, or I'm going to write 0.4. If I plug in 0, I'm going to get 1. If I plug in 1, I'm going to get 2.7. The horizontal asymptote, there's no vertical shift, so it's y is equal to 0. The domain is -infinity to positive infinity for all exponential functions, and the range is 0 to positive infinity. If I wanted to find the inverse, sorry, I have to graph this. I have the horizontal asymptote, so I'm going to draw that. It's y is equal to 0. That's my horizontal asymptote. I have the point -1 and 0.4. I have 0 and 1 and 1 and 2.7. I'm going to connect these, making sure I don't touch that horizontal asymptote, and that's my graph for the exponential function. For b, I want to find the inverse. All I'm going to do is take this exponential function and change my x and y, so I'm going to end up with x is equal to e to the y power instead of y is equal to e to the x power. To rewrite this inverse in logarithmic form, because I need to get that y by itself, and that's the only way that I can do it is convert, I'm going to have log base e of x is equal to y. So I had my base was e, my exponent was y, that's what the logarithm spits out, and then the answer is what's inside of the logarithm. This is another thing like we talked about with base 10. If you have base e, this is called the natural log. So another way to write log base e of x is just to write it as ln of x. So the log base e changes to ln, and this is something I'm going to do when I see log base e. ln is the natural log. The natural log is to base e. And so another way that I could write this, instead of log base e of x is equal to y, I would write ln of x is equal to y. So I just have to write the answer inside and the exponent on the outside. I don't need to write the base. Making a table for this, I'm picking values of x to plug in and seeing what I get for y. I'm going to use this version of the logarithmic form. So I'm going to pick values for e to plug in. I'm going to pick values for x to plug in, and I want to pick powers of e. So I'm going to do first log base e of e to the -1st power. And if I do that, I know it's going to spit out y is equal to -1. So if I do e to the -1st power, it's -1. If I do log base e of e, 1, I'm going to get y is equal to, what do I have to raise e to get 1? And that is the 0th power, so y is equal to 0. If I plug in 1 for x, I'm going to get out 0 for y. And then if I do log base e of e to the 1st power, that's going to spit out y is equal to 1. What do I have to raise e to get e to the 1st power? So I will have, if I plug in e to the 1st power, I will get out 1. And another way to simplify all of that, if I had the function, I'm going to erase this here. If I had the function y is equal to, I'm going to write ln of x instead of all of this. I'm going to have my table is going to be e to the -1st power is 0.4, and then I'll have -1 for y. The next point is 1 and 0. I'm just bringing over this table and simplifying. I have e to the 1st power is about 2.7, and I'll have then 2.7 and 1. I can look that this table is the inverse of this table. The x's and y's are flipped. I have my vertical asymptote because I know I'm changing everything about my x's and y's is changing. I'm changing from my asymptote being at y is equal to 0 to x is equal to 0. I know the domain is going to be, I know this is the inverse, so I know the domain is going to be 0 to infinity since the range here was 0 to infinity. And I know the range is going to be negative infinity to positive infinity because that's always the case for logarithms. The vertical asymptote, I'm going to draw it at x is equal to 0. And then I'm going to make sure, I'm going to plot my points, 0.4 and negative 1. I have 1 and 0, and I have 2.7 and 1. And I'm going to connect these, making sure they don't touch that vertical asymptote. I can see these are a reflection over the line are y is equal to x. So I know based on these graphs, everything about the x's and y's being flipped. I know y is equal to e to the x power, and ln of x are, or log base e of x are inverses. When I'm graphing equations that have ln in them, I am doing the same thing as with logs to other bases. I just need to keep in mind that when I see ln, that means that I have log base e. So for the second example, I would have, instead of ln of x plus 3, it would be log base e of x plus 3. The parent function, or the parent exponential function that I'm going to graph, the inverse of the logarithm that I want, is going to be base e. So I'll have y is equal to e to the x power. We've made this table a ton of times before. We're going to pick negative 1, 0, and 1 for our x values, and we're going to get out for our y values about 0.4, 1, and about 2.7. From here, we would convert to our parent logarithm, which is the inverse of that exponential function, and the logarithm we're looking for to do transformations to. And that the inverse of y is equal to e to the x power is y is equal to log base e of x. We're going to just write y is equal to ln of x instead of log base e of x. And all we're doing is flipping the values that we see here in this table. Our x's and y's are flipping, so we'll have 0.4 and negative 1. We're going to leave enough space because there's a horizontal shift here. We have 1 and 0, and 2.7 and 1. And this shift that we see, this plus 3 inside of the logarithm, tells me that I'm moving to the left 3. If I move to the left 3, that affects my x values, and it means that I'm going to subtract 3 from all x's. That's how it's going to affect my x values, from all x's. So I'm subtracting 3 from all my x's. That's going to give me my final log. So that's going to give me my final log when I apply those transformations, and I'm going to have y is equal to ln of x plus 3. That's the shift of everything to the left included. That's my equation for that. And then I'm just going to do these transformations. So my first point is going to turn into negative 2.6 and negative 1. My second point is going to be negative 2 and 0. And my third point is going to be negative 0.3 and 1. Before I plot this, I'm gonna draw my vertical asymptote. I know that everything's moving to the left 3, so my vertical asymptote, since I have a logarithm it's vertical, is gonna be at x is equal to negative 3 instead of x is equal to 0. So that's x is equal to negative 3 is my vertical asymptote. And then I'm gonna plot my points. So I have negative 2.6 and negative 1. I have negative 2 and 0, and I have negative 0.3 and 1, and I'm going to connect these, making sure I don't touch that vertical asymptote. The domain is everything from negative 3 to infinity, and the range is negative infinity to positive infinity, always for logarithms. I want you to try this example.